it has a unit of delta H. And I'll probably try to say it a couple of times, but we're going to have a term that's known as enthalpy. We're going to have a term that's known as entropy. And so it's important to get your definition straight. Now, the difference between Q versus enthalpy, we need to have a variable that will deal with heat transfer in situations where we are not keeping temperature and pressure constant, okay? Out there in the real world, you know, if you're talking about refrigerators and things like that that work by compression, then you're going to have a variable for Q. You're going to have a variable for when temperature and pressure are kept constant, okay? And so in most first-year chemistry books, we do say, okay, we're going to have a constant temperature and pressure, and then Q and H are used almost interchangeably, and I feel like that's what confuses students. So I'm going to try to give you a few guidelines. Delta H is almost exclusively used when you're talking about chemical reactions or the heat that it takes for something to dissolve, okay, which doesn't always look like a chemical equation or sound like a chemical equation. The heat for something to combust, the heat for something to go into solution. And Q, we use a lot in calorimetry. So if you have a hot object and you turn it and you drop it into cold water, what's the heat transfer? That's a lot of times what we use Q for. But sometimes chemists tend to assume that they know what they're talking about, and sometimes it does seem like Q and enthalpy are being used interchangeably, and so just try to keep in mind that some of that is due to the fact that in this particular context, we're assuming that temperature and pressure are constant. Yes?
So for our purposes, are we going to say Q is enthalpy, represents enthalpy, or Q is a completely separate variable?
So for our purposes in this class, they can represent the same thing. Okay? And so I feel like that's what sometimes some of the confusion is. So if you in your lab calculate the heat transferred, it's called Q, and then all of a sudden somebody's saying, okay, so what's the change in enthalpy for the chemical reaction? That's the kind of thing that happens that confuses students. Okay? So I'm just trying to move forward, review a little bit, and then talk about what I've discovered that is confusing to students. Okay? Any other questions? I know we haven't gotten very far. So there's the first law of thermodynamics. Work. So up here was our definition. The change in internal energy is equal to the heat transferred to the system plus work done on the system. So here we have the change in energy is equal to the heat plus the work. Okay? And if it's any consolation to you, you won't have to do any change in energy. A lot of this chapter is trying to set down definitions. So a lot of this is going to seem like it's kind of slow going because we're going to kind of be reviewing and setting down definitions, okay? And that's just the way it is. So here, the second law of thermodynamics. The second law, and here we introduce a new topic. It's the total entropy of a system and its surroundings always increases for a spontaneous process. And that's the second law of thermodynamics. So, briefly, what is entropy? and we're going to delve into some of these a little bit more. Entropy refers to the randomness or disorder in a system. And just like enthalpy, it is a state function. Now, don't get weirded out. It's not like you're going to have to do graphs or anything like that. A state function simply means that it only matters where we are. It doesn't matter how we got there. Okay? And what that means is that we can only deal, you'll notice that these deltas refer to change in entropy. So we can only deal in changes we can't deal in some absolute entropy. And you'll recall that this is a similar analogy to when you studied enthalpy, when you previously studied heat, right? You can't say this is the enthalpy of the system. You can only see how it changes, right? You have an initial state, you have a final state. So I don't know if this is helpful. This is all it means when it's a state function. If I have a person here who's on top of this mountain, okay? There's no way, if I just have a snapshot of them standing on that mountain, I have no idea whether they very arduously climbed up this mountain or whether they parachuted out of some airplane. All right? They could have parachuted out of the airplane and ended up on top of that mountain, right? Okay? So I can't talk about this person just being at the top of the mountain. And when we're talking about energy, I have to talk about it in terms of not just where they ended up, but where they started as well. So all three of the thermodynamic functions that we are going to talk about, enthalpy, entropy, and then we're going to define what's called a Gibbs free energy. It's the Gibbs free energy that's going to tell us definitively whether something is spontaneous or favored or not. But we haven't even gotten there, so don't get too... Now, this randomness or disorder in a system, books vary by how much they want to convince you that it's really mathematical, okay? For the purposes of our class, if you're the kind of a person who likes to really understand the background of these things, entropy is a very it's a very mathematical type calculation. Your book gives the actual calculation. You take all the places where energy can exist, and you see whether you have more or fewer when you're all done. And entropy is sometimes, so if you have a really messy bedroom, okay, that's the spontaneous process, right? What do you have to do to clean up your room? You have to do what?